All right, so I guess let's talk about simple harmonic motion. So I guess this is something that you've kind of touched on in physics before. What were you kind of saying about it before, Matt, that you'd learned about? Yeah, right, okay. So now this is something that I actually kind of learned when I started teaching simple harmonic motion, is that although we typically model simple harmonic motion using sine and cos waves, right, that's actually not its definition, right? So if you want to think about the situations that typically model simple harmonic motion, like what are some examples? You've got a spring bouncing up and down. What other things could you have? Maybe like a boy bouncing up on a wave or something like that. Any other examples you guys looked at? What was the ones you were saying before? The this guy.
Pendulum.
Yeah, now a pendulum's something a bit strange because actually if the angle is large enough, it's no longer modeled by simple harmonic motion. It has to rely on a very small angle that's being created, and that's related to a trig property where sine theta is equal to theta for very small angles. That's kind of a bit out of the scope. But the definition of a simple harmonic motion is if its acceleration is at any time proportional to its distance from the origin. Right, so if you want to think about what that's kind of saying, if you think about having a spring, and you think about the further away it gets from the origin, right, you can see that the acceleration is going to be affected by that. Because like the more that you pull it away, the more it wants to kind of bounce back up to its original point, right? So that's the kind of idea, intuition behind it. And as you'd expect, we tend to model these with the trig curves. And when we think about using our trig curve, so cos x or sin x, or I guess in terms of t actually really, right, because we're looking at in terms of time, what you want to think about is, okay, modeling this in terms of time, and I'm using a trig curve, but sine and cos, they're slightly different, right? Cost, yeah, cost functions, right? Looking at that in standard. So when you think about your trig curves, think about what this is representing in terms of its starting point, right? So sine would be if it's starting its motion at the sort of origin, or really the center of motion actually, right? But where is cos starting from, if you think about it? Yeah, and extremes of, we call these extremes of motion, yeah? So if it's starting at the extremes of motion, then we use cos to model that. Typically we will use cos to model curves in simple harmonic motion. It actually doesn't really matter for your calculations, but for the most part we do use cos, right? Now, one thing I want to talk about that's really important is that we've been talking about motion in terms of time for the most part in these courses, right? But because we have a definition for simple harmonic motion now where its acceleration is proportional to its distance from the origin, can you see how what we learned last lesson when we were looking at defining acceleration, not in terms of time, but in terms of what? What do we look at? Displacement, how that's actually useful. And that's actually the definition of simple harmonic motion. It's not that if I just have a sine or cos curve, then it's in simple harmonic motion. That's how we tend to approach the problems, but this is its definition. And there are going to be some problems that you'll get where it doesn't involve any trig kind of curves, but it satisfies this definition. So I'll show you the definition that they give you. So something is in simple harmonic motion if it satisfies this equation here. So this is simple harmonic motion about x is equal to 0. Our acceleration will be equal to minus n squared x. Okay, so you can see that x is our displacement, x double dot is our acceleration, and n is some constant here. Does n have to be greater than 0? Let me double check for you. Sometimes they do specify this. Yes, so n greater than 0. N has to be greater than 0. Okay. Now, if you want to think about why this might be, I'll show you the proof for this, and I'm going to do another proof a little bit later on. But if we just think about our cos curve, right? So let's look at x is equal to, now I'm going to manipulate this in a few ways. I'm going to use a capital A here, because I always get it confused with the alpha. So this is our general kind of displacement curve. If you want to think of that, you've got x in terms of time. Well, I'm going to use cos because that's the default usually. Just think about some general properties. Right, we know a is the amplitude. What would be the period for this guy? What's the period of this kind of curve? Yeah. So think about just your normal trig properties, right? So it's just 2 pi on n. Now be careful with this one. What is the phase shift? So how much has it been shifted by? Yeah, so this is where actually advanced transformations actually comes into useful. You can't, when you're looking about the transformation, the phase shift, you don't want to just look at the alpha value because there may be a coefficient here that's affecting that, right? So actually it's better to write this as, I'm running out of room, I'll write it in here. N outside of t plus alpha on n, so you kind of factorize out the n, and that way you actually get the phase shift that's occurring, the phase shift of alpha on n, yeah? Okay, so we're only kind of looking at the amount here, not really direction because, trig curves, they're sort of, they're symmetrical in some sense, so a bit hard to think about that way, but yeah. So there's just some general info. Where does this sort of come about? Well, the idea is if this is my displacement curve for some simple harmonic motion that's being modeled, right? If you take its derivative, that's just derivative cos I know is negative sign. So a is a constant where a is the amplitude, right? So a also has to be greater than 0. Alpha, yeah, that could potentially be negative. So I don't think there's any condition on that. But let's look at this one. So if I take the derivative here, I get sine. Oh, hang on, no, then. What do I actually get? an, thank you, sine nt plus alpha. Okay, looks pretty good. What if I take the derivative again? Yep. An squared, good. So an squared cos nt plus alpha. And so you can see where the this sort of definition comes from now, because this is your acceleration, right? But you can see that that's actually the same as what you have over here. This is just a times cos nt plus alpha, which is, as you said, Matt, that's just x, right? So that's also equal to minus n squared x, all right? Questions about that? No? You want to jot that down for me? So why I'm showing the proof is a common type of exam question, actually, because they'll often ask you, prove or show that something is moving according to simple harmonic motion. It's not enough to just say, oh, it's a trig curve, so it is simple harmonic motion. This is the condition that needs to be satisfied. This is about at x equals to 0. I will show you what happens if it's sort of been shifted around a little bit. Yeah, so I'll show you that in a bit later, though. Remind me. But